This is Knowledge Engineering with Semantic Web Technologies, Lecture 4, OWL, Rules and Reasoning. And this is part 14, an extra part about rules which are expressible with OWL. And this is also the last part of this lecture number 4. Okay, in the last part we had seen that swirl in general is undecidable simply because it combines OWL ontologies with data log. But we also have seen that for practical reasons, nevertheless, you can work with swirl simply then by restricting swirl in some way. Okay, so the next thing we want to look at is which swirl knowledge bases enable complete inference algorithms. So we want to somehow shrink or reduce the expressivity of swirl, or we want to apply tricks really to be able to guarantee that the inference algorithms will work. So how can we do that? One possibility could be, of course, if we only take into account swirl knowledge bases which exists only out of OWL or OWL2 axioms. So there are no rules. Then, of course, we have complete inference algorithms, as long as we do not consider OWL full, but only OWL-DL or one of its profiles. Sure, this is trivial. The same holds also if we consider knowledge bases in swirl which only consists of set of data log programs or data log rules. This is also trivial. Also, if you combine both of them and if you only consider so-called static finite classes in swirl, so they don't, for example, contain existential quantification, so no implicit individuals are contained in there, they are static, so there can nothing be assumed or implied, then these kind of knowledge bases also guarantee complete inference algorithms. But the question remains, can we do more than that? Yes, we can. There are more swirl fragments that are decidable. And at least about two we want to talk in this part, in this last part of the lecture. The first one are the so-called description logic rules, which are swirl rules that can be already expressed with OWL2. So we will identify which kind of rules this property really applies to. And the second one are the so-called DL safe rules. So here we introduce a restriction to rules via variable assignment constraints. So this is a trick to guarantee so-called DL description logic safety. So we guarantee here via this trick complete inference algorithms. But first, let's start with the first one, description logic rules. Okay. So the general idea behind that, so you see here this has been introduced in 2008. The general idea here is we have to find out which kind of rules can be expressed via OWL. So simply, of course, if you look at these simple subsumptions, so here at class subsumptions or property subsumptions, of course they can be easily translated into appropriate rules, as you see here. And of course you can also extend this schema a bit. So some classes can be fragmented into rules. Let's have a look at these classes. Here, for example, in the first class expression on the left side, we have two classes which are disjunctive. And of course, you can translate this in a rule and you can say, so if X is of class A and X is of class B, this implies nothing, the bottom element. So this means both classes A and B are disjunctive. There is no individual which can be at the same time part of two classes. So this is an easy translation. Another kind of translation would this be, so here you have a simple subsumption where on the one hand you have a class A and you say A is subsumed by, and then you have a universal quantification. So this defines a class for which all applications of the property R result into a class B. And this simply can be translated in if the individual A is of class X and you have the property R applied to X results in Y, then of course Y must be of class B. This implies that Y is of class B. So also here you see simple kind of translation. It also works if in the superclass, for example, here you have a disjunction. This can be translated into a rule in the following way, that you say, okay, if X is of class A and X is of class B, then x must be of class C. Simply because this fulfills also the other side of the equation, or this fulfills also the description logics expression that we see here, that A is subsumed by not B or C. This is interesting. So this one is, for example, R is defined as being a functional property. So it means that the result, or it can only be, if it's applied to an individual, then of course the result, it's only mapped to one other single individual and not to two or more. So you can translate this simply in the following way. If you say if X is mapped via the property R to Y, and X is mapped via the property R to Z, it must hold that Y is equal to Z. So this is functionality. And this one is another one. It's a bit more complicated. You have here, for example, A. So the complex part is here in the subclass expression. So on the left side of the subsumption relation, you say here X is of class A, and X, if I apply the property R on X, this results in Y. And then if I apply on Y the property S, this results in Z. Then Z must of class B. This implies that X also is of class C. So you see here, this is a rather complex expression. And of course, you could also extend this kind of chaining of properties here. So these kind of classes can be translated into rules. So, and this of course are already sophisticated rules, as you see here. So we can continue this a little bit. For example, you can also integrate quantifiers into these rules. So for example, on the first rule you see here, we have an existential quantification which applies to a class here, or which restricts to a class which only consists of one individual. So this is a nominal. And this, of course, can easily be translated in the following. If you say the individual X must be of class A, and then I apply the property R to X, and the result will be an individual, which is B, then X must be of class C. So this is the simple translation for that. Then, of course, you also can adapt equivalence. If you say two classes are equivalents, and if these classes only consist of single individuals, then, of course, you can translate this into the fact that A is equal, the individual A is equal to the individual B. Let's have a look at the next one. Here you have in the superclass a conjunction. Then, of course, you can split this into separate rules, which are connected by both must hold, so they are connected by and. So if X is of class A, then X must be of class B. And, of course, if X is of class A, then X must be of class Z. On the other hand, also, you can have disjunctive classes on the left side, so on the side where the subclass is in the description logics expression, and then you connect these two rules simply by an OR expression. So one of the both then in the end holds. So in general, if we try to generalize this, means if we have a description logic axiom alpha, this can be translated into rules if after first translating alpha into description, if after translating alpha into first order logic expression, alpha prime, and then after normalizing this expression into a set of clauses M, each formula in this set of clauses must be a Horn clause. So then you can have this simple kind of translations. What it does not contain are, for example, complex properties which consists out of property chains. And for property chains, we have to extend somehow our OWL description logic. So we do not really extend it, we simply use a trick, as you see here, that we can also make translations between rules that require property chains. Let's have a look at some examples for that. So here, for example, very easy example. we have a property chain for the expression uncle. We say has parent connected to has brother. This is a subclass of has uncle, which means if X has parent Y and if Y has brother Z, then X has uncle Z. So it means in general, you can simply translate, of course, a property chain, as you see it here, into a simple conjunction of properties applied to a sequence of individuals. And you can, of course, express this then as a simple rule. This is quite easy as long as in your property chain there are only properties. Of course, in a property chain there cannot be classes, but if you consider vice versa a rule, in the rule instead of one of the properties there could also be a class. So is there then any way to retranslate that? Let's have a look. So for example, what if on both sides of the rule there are not only properties or not only classes? So we have here a nice example. We say X is a man, and we say X has a child Y. Then X is the father of Y. So we have on the left side in the body, we have a class expression which is combined with a property. And on the right-hand side in the header, we only have a property expression. So how do we express something like that in our tool? So usually via property chaining, as we see, this is not possible because man is a class and not a property, so therefore we cannot chain it. How can we connect it? So the solution is the following. What we do here, we simply substitute the class man with a property expression to make it a property chain. And this property is formed by applying the self-restriction to transform classes into properties. So we have an auxiliary property which is called P sub man, which is our auxiliary property. And we introduce additionally an auxiliary axiom which says that man, the class man, is equivalent to this expression that you see here. And you say there exists some, or this is an existential restriction of the auxiliary property P on itself, which means if I use X here, then of course this is a class expression which results into X and nothing else, so on itself. And then I can use exactly this auxiliary property in a property chain to express the very fact that P-man represents the class man, but of course it's expressed as a property here. And therefore I can express exactly these kind of rules with the help of a property chain. So P-man connected to has child is a subclass of father of. So this would be the correct translation of the rule you see here in blue into a description logic expression with the help of an auxiliary property plus an auxiliary axiom that you use. So this is a bit complicated, you have to think a bit about it, but it's clear you have somehow to transform a class into a property, and you do this via these auxiliary constructs. Are we done? Yeah, there can of course be other combinations of classes and properties. Let's have a further look. So in general you say, okay, this is called rolification of concepts or classes. So first let's have a look at the general case again. So here, for example, we have a rule which first consists of a class connected to a property which results into a new property. And of course this can, with the help of our rolification or of our auxiliary property and auxiliary axiom, translated in what you see on the right side. So this is the simple case. Of course we can extend this a little bit. The class expression of course could also refer to the result of the property, so to the Y part. Of course this works in exactly the same way, so then I can do in the description logic part, I can do there a property chain where our auxiliary axiom is in the second place. So it's quite similar and straightforward. And the same also is possible if we have classes for both, which are the first part and the second part within our property expression. then simply I combine it in the way you see here. I start with an auxiliary axiom for the first part of my property expression, then comes the property, and then comes the auxiliary property for the second part, or the second variable that is used here within the property. And this results then in a new property S. So this is the generalization of the rule. There can be even more cases. Just have a look at that one. X is a vegetarian and Y is a fish product. And if X is a vegetarian and Y is a fish product, then usually X does not like Y, simply because he's a vegetarian or she's a vegetarian. The problem that you see here is on the one side of the rule we only have classes, and on the other side of the rule we have properties. We can't express this simply as a property chain, and we can't express this simply as a description logic statement, simply because then on the one side of the subsumption would be properties, on the other side of the subsumption would be a class or would be classes. How could we do that? Okay, so for the classes, somehow we know this trick already, we could use a role. The problem then is how do we connect these roles? Because if we introduce an auxiliary property for vegetarian, there X would be mapped to X. And if we have a fish product Y and we have an auxiliary property for fish product, then Y would be mapped to itself, to Y. The problem is X is not equal to Y because X is a vegetarian, Y is a fish product. How do we connect them? So the properties cannot be simply connected, like in the rules we have considered before. How do we do that? For this, we introduce or we apply something which we already know from OWL. We have introduced in OWL a so-called universal property. We have in fact two universal properties, a universal object property and we have a universal data type property. And via that universal property we are able to connect any other property. And here we can make use of it. So we have two auxiliary properties, one for vegetarian, one for fish product. Each of them maps a variable X to itself. And we connect this simply via taking the universal property U in the middle of both of them. So simply because of that, we can map with a universal property X to Y. And we construct a new property chain from vegetarian over the universal product, universal property to the fish product. And this, of course, then constitutes our new property that we define here, which is the dislikes property. So this would be the translation for exactly this situation, where you have on the one side only classes and on the other side properties. So this would also work if you switch all this stuff. Are we done? Is this simply all, or are there things that we haven't considered so far? I can show you one specific example. So there are, of course, more problems. Just have a look at that one. This looks easy, doesn't it? So we have here, X has ordered a dish Y. And X does not like Y, unfortunately. Then this results into a new class, which means X is unhappy. So on the one side, properties, they are connected. On the other side, a class, a simple class. How do we translate that? So this is really some tricky case. And I can tell you in the end, it's not really possible to do this with OWL DL. The reason for that, so you can try this, somehow you must eliminate the variable y in the middle of both when you connect these two things. And there you see we will have some difficulties by doing this. So for example, if we try to do it in the following way, if we say, okay, somebody has ordered some dish and somebody does not like something, then he's unhappy. Yeah, but this does not work simply because we do not here connect X to Y, and then of course we are not sure that X and Y in the dislikes part are exactly the same. So this is not possible. We must make some connection where these two properties somehow are used together. So one possibility could look like that one. So what about this one? Yeah, so here we have ordered dish, so X has ordered dish Y, and we look at the inverse of the dislikes. And there we can say, of course, Y is disliked by, simply by X in the rule, but not in the description logic case. In the description logic case, Y could be disliked by anyone. So there is not necessarily a binding for the variable X here in that expression. Therefore, this is also not possible. And you also cannot do this with the help of a property chain. Simply then you have property on the one hand, class on the other hand, on the other side. So this is a case which is really difficult and which is not possible here to cope with in the description logic rules. For this, you need something else. But in general, now we know which kind of rules can simply be translated from swirl into OWL, into description logics, and which therefore are decidable if we want to apply some of these standard algorithms. Okay, let's have a look at the second part, or at the second fraction here, the so-called DL-safe rules. Here we want to restrict swirl rules via so-called variable assignment constraints. Okay. The basic idea here is that we restrict swirl to guarantee decidability, and we do this by restricting the number of possible variable assignments. So usually the arbitrary data log rules are allowed with names of OWL classes and OWL properties. But to be DL safe, each variable must also be represented within an expression of the rule body that doesn't use an OWL class or an OWL property. So what we want to do is we want to restrict the application of OWL axioms and rules only to known individuals, which means we do not want to implicitly talk about potentially existing things. So we want somehow to overcome this open world assumption with this, in or by restricting really the application of our expressions to known individuals. And then we can simply apply the entire semantics that we have, and with the help of this trick, of course, we can apply all possible inference rules, and they are complete. So how do we force this DL safety? Let's have a look at the following example. So this is a simple, you see here, chaining of properties. We say X has father Y and Y has the brother Z. Then X has the uncle Z. How do we now force DL safety? Usually they are not DL safe simply because the expressions I use here in my rule are OWL properties. So potentially there can be an individual that can be by some other expression implicitly deduced. So we have to force here and restrict the rules to known individuals. And you can do this, for example, by introducing here new class expressions for all variables that you use in your rules, and then simply say for all individuals, for all OWL individuals that you consider that are part of your knowledge base, this fact, this O of A, has to be asserted. And then you restrict, of course, the application of this rule exactly to these individuals that comply to that and that are really existing. So non-existing individuals, which are somehow only implicitly referred to, are explicitly excluded by here. So the rule is only applicable to known OWL individuals, to named individuals. Here we have an example of that. So we force DL safety. The example, simply we want to express he who hates his brother is evil. We know two people are brothers if they share the same father or the same mother, for example. And in our knowledge base, we have the following expressions. We have Cain has the father Abel, and we have Cain has the father Adam, and Abel has the father Adam. Then we have also Cain hates Abel, and then, because not only we have Cain and Abel in our database, we also have facts about Romulus and Remus. And we have here, for example, there exists a father, which again has the inverse father of Remus and Romulus. Simply try to find out that both of them have the same father, but we do not know who is their father. Of course, from mythology we know that, but in our knowledge base we don't know. But what we know in our knowledge base is that Romulus hates Remus. So then let's have a look at the following rules. First at the black rule here, which says if x has the father z and y has the father z, which means both have the same father, so they are brothers, and x hates y, then x is evil. And by that fact, of course, we could deduce from that knowledge base that Cain is evil, as well that Romulus is evil, as well as Abel is evil. The point is, of course, if we apply this to our individuals, our concepts, then it's not DL safe. And now we enforce DL safety simply by introducing this class expression O for all of the variables that occur in the rule, which are x, y, and z. And then this would result in an evil expression or evil property which is DL safe. So if you look at the instantiations for all our known individuals here, of course we can instantiate O for Cain, we can instantiate O for Abel, for Adam, for Romulus, and for Remus. But of course not for the father of Romulus and Remus. And simply therefore, safely it can only imply that Cain is evil, but it cannot be implied that Romulus or Remus is evil, simply because we have no individual in the knowledge base which could comply or which fulfills the requirement that it is the known father of Remus and Romulus. So this would be an example of forcing DL safety. And this is another way somehow to guarantee the completion of algorithms and to guarantee decidability for swirl rules, which are expressed here again as or with the help of OWL and description logic. So let's sum up everything. Rules and the semantic web. So we have swirl, which is a combination of OWL and data log, and swirl usually is undecidable. We know that. To guarantee decidability, we have learned about two specific procedures. First, we have description logic rules, which means we simply looking which kind of swirl fragment can be expressed with the help of OWL. And this, of course, is supported by OWL2 Reasoner, so you can apply this. And the other variant was the so-called DL safe rule. So this is a swirl fragment where variables only can be assigned to concrete values. So we look at really known individuals which are part of the knowledge base. This is also supported by OWL reasoners, and therefore DL safety can be forced. What is still missing, and this of course is part of ongoing research, so standards and best practices for rules, they still do not exist for the semantic web. So therefore, this is still ongoing research. Okay, and with this, we have finally finished also the fourth part of the lecture, so lecture number 4. And next, we will start lecture number 5, which then will cover ontological engineering.